As Dr. Foster said, this is our first Oxbridge Network lecture, and today I'm going to be presenting about identities and personalities in elementary algebra. I'll tell you a little bit what I mean in just a moment and what's involved in all of that. So what I'm hoping to do with this time is explain a little bit about where some of the mathematics that you study in school goes once you leave school and go off to do mathematical things at university, and also a little bit about where it comes from. So mathematics doesn't exist in isolation, but rather it was invented by people, discovered by people across the world over various periods of time. And I'd like to just pick out a few examples to illustrate that point. So I guess to start with, it's worth me making my definitions clear. And for me in this talk, when I'm talking about a lecture, an identity, we're going to be talking about a statement of mathematical equality that is true for all possible values of the variables. Now, obviously, that's the mathematical definition of identity, but it also relates to what or who a person is as well. And I'm going to try and draw out some of those links as we go through. Now, this talk is primarily aimed at sixth formers with an interest in the mathematical sciences. So get your hands dirty. There will be some mathematics involved in the actual lecture. But I'm anticipating that it's not going to look like this in terms of difficulty against time. It's not going to start off easy and get harder and harder and harder as we go. It's also hopefully not going to look like this, which is what my experience of some math lectures is, where it starts off okay, you get to grips with some ideas, and then suddenly in the last 5 minutes it all explodes and becomes incredibly complicated. I'm going to try not to do that either, but rather, because we're interweaving some history and some mathematics as we go, it hopefully will look rather more like this. So you'll get to find out a little bit about the characters, a little bit about what motivated them, look into some of the mathematics. It might get a bit sticky, but cling on as best you can. And if you drop off the back of the bus, then don't worry, there'll be another one coming along in just a moment to help you along. Dr. Foster, just as I'm presenting, I'm getting a few notifications that people are entering via the lobby. If you could handle those, just let me know. I
have actually handled them, Mr. MacArthur. So
Perfect.
Every time I get a notification, I let them in. OK,
great.
So you don't need to be bothered by that at all. OK,
perfect. Thank you very much. OK, so that's the idea. How is this talk going to be structured? Well, I've taken my inspiration from this excellent UK Maths Trust book. I got in contact with Dr. King to find out whether he thought this was a good idea. He has nothing to do with the talk. All the mistakes are going to be mine. It's an excellent book which would help any student in the sixth form who's looking to do well in Olympiad problems, specifically with a focus on the algebra ones. So if you've just recently sat the British Maths Olympiad, or you've been doing the senior maths challenges and want to push on to the next level, I'd recommend all of these kinds of books. And this is the one that's inspired my talk today, because in the very first exercise, we get this marvelous list of algebraic identities. So these are things which should be true for all the values of the variables which are permitted. And you can prove them. Sometimes they're easy to prove, and sometimes they're difficult to prove. But there's a list at the front of this book of things that the author thinks you should know. And when I was going through this list, I noticed that a fair few of them are familiar to A-level students. Some of them could be familiar, but then not so much. And then a chunk of them in the middle, these ones here, all had interesting names related to their history. And these are the ones that I'm going to focus on today in my talk. We'll look at Babylonian multiplication, Cardano's identity, Sophie Germain's identity, and then Diophantus and Brahmagupta's identities as well. We won't take them in that order. We'll take a more chronological approach, but it will take us on a journey from Mesopotamia to Italy across to India and Egypt as well. So it's a broad tour that's going to lots of places. Okay, let's start off with a more gentle mathematical warm-up though. Hopefully the first of these expressions, these identities, is something that you recognise. If you're studying A-level maths, hopefully you met it at GCSE, the difference of two squares factorisation. Question naturally comes up, is it just the difference of two squares that we can do like this? And if not, how do we factorise it? What should go in that second bracket, assuming that the first bracket is even right in the first place? Now, if we take a guess that a minus b is going to be a factor, it seems plausible that we could fill in the rest kind of step by step in a way that resembles algebraic division. So we've got a minus b as that first bracket. We want a cubed minus b cubed. So we've got to decide what goes in the second bracket so that when they multiply together, we get the first bracket. In other words, what do I put here so that this here times by the things in here gives me what I need? Okay, well, let's try an a squared to start with, and that's a useful thing to do because it will create the a cubed on the front. Okay, so it creates that a cubed that I wanted, but I've also got this minus a squared b as well, which I didn't really anticipate. So it'd be a good idea for the next thing in the bracket to get rid of that negative term here that I don't want. So I'd like to put something up here so that I can get rid of the minus a squared b that I just added. Okay, well, let's put ab in its place. Maybe you spotted that. Maybe that was an easy thing to think. Maybe now that you've seen it, you'd expect it. So why does this seem like a sensible thing to do? Because when I do a times ab, then it gives me a squared b, and that will cancel with the thing I already created, but I've accidentally created a minus a b squared along the way, which I didn't want. So now I have to worry about getting rid of this bit here instead. So how does that work? Well, let's just put a b squared on the end, see if that helps. Now a times b squared, that looks hopeful because that creates this term down here, and we've got a minus b cubed. Okay, so just to summarize what we did there, we were looking for a bracket that we could times by a minus b to get a cubed minus b cubed, and each term in yellow and then green and then blue has contributed all of these parts in yellow and green and blue. Now, all the terms in the middle, apart from the a cubed and the b cubed, we designed them such that they would all cancel out, and so we know that this identity is true. So we've managed to work out an identity for a cubed minus b cubed. That's one of the ones that's in Dr. King's book. So having worked out this identity, it turns out that if we flip the signs of this identity, then we end up with another true identity. I'll leave that one for you to verify for yourself if you haven't done so before. But what this means is for cubes, we can always factorize the difference of two cubes and also the sum of two cubes. And in many mathematical problems, being able to factorize things is useful, so this is going to be helpful. I think it leads to a natural question now. If we know that we can factorize the difference of two squares from GCSE, and if we've just seen that we can factorize the difference of two cubes and the sum of two cubes, is it reasonable to assume that we should also be able to factorize the sum of two squares? And very often at A level, if you don't go on to study complex numbers, you'll be told this fact, that the sum of two squares cannot be factorized in the same way as we can for the difference of two squares. And the question is that really true? And if you know about complex numbers, then you know it's not true for complex numbers. But as written, I also want to claim that it's not quite true even for real numbers, so numbers that live on the number line. This seems to be a counterexample, for example. In what sense is this a counterexample? Well, if your teacher tells you that the sum of two squares can't be factorised, you might turn around to them and say, well, when I take 3 squared and add it to 4 squared, I get 25, which I can definitely factorise as 5 times 5. So something is a little bit awry there. Sometimes it looks like you can factorise a sum of 2 squares. And it gets even worse if your teacher is maintaining that this is absolutely the case in all circumstances, because here's a factorisation I can write down that is going to be true for all values of a and b. This is another identity. It works. Just multiply out the right-hand side and you'll see. But your teacher isn't entirely wrong. They are actually right in trying to help you when they say they can't factorise a squared plus b squared. But it's a little bit more subtle. What we really mean is that the sum of 2 squares cannot be factorised in the sense that there's no algebraic identity for factorising the sum of 2 squares as a product of linear factors with real coefficients. What does that mean? Well, these terms here in the brackets are not linear because they involve square roots. And we can't guarantee when we take a square root that that's a whole number. It's not a linear amount of a and b. So this is what your teacher means when they say you can't factorise it. You can't write down something nice like we could for the difference of squares and the difference of cubes. So when we write down the difference of squares, we get a nice factorisation that doesn't involve any square roots, doesn't involve anything other than linear amounts of a and b. And when we're factorising a cubed and b cubed, we're factorising it like this, and then we're getting terms that involve only integer powers of a and b. Right, so we've seen this, the difference of 2 squares. I proved this, the difference of 2 cubes. The natural generalisation is to look at the difference of 2 powers of a and b. This one I've just included here because I think it's worth knowing that regardless of the power, you can always write down this factorisation. This will work for when n is 2, 3, 4, 5, 6, 7, all the way up. You can always take out this linear factor a minus b, and sometimes that will help you solve a maths problem. Okay, so we've got this fact for the difference of 2 powers. We've got a very related fact for the sum of 2 powers, but this is only going to work in the case where the power is odd. And that's why I've written it in this form, 2n plus 1. So the sum of odd powers of a and b can be factorised out like this. Okay. I promised that this would go up in and down in waves. If you followed all of that, fantastic. We've got off to a great start. What we're now going to do is head back in time a little bit and talk a little bit about Babylonian mathematics. So what we're talking about here is a civilization that was flourishing maybe 3,000 years before the Common Era, and sometime around 1700 BCE, there was a civilization based in Babylon that conquered the whole area. And they had such success in taking over this area. They had a professional army that helped them achieve that. But on the back of their military success, they ended up developing a very intense cultural life as well. So they started experiencing economic growth that allowed a middle class to develop. So they had merchants and artisans involved. And also on the back of a coordination problem of needing this large expanse of area to be effectively governed, they started to make intellectual progress as well. They needed to start keeping accounts of everything that was going on. They invented writing as an accounting tool to enable them to keep records of taxes and amounts owed and so on. And we know masses about this Babylonian civilization thanks to the fact they recorded all of their information on these clay tablets. Sometimes they're made of clay, sometimes they're made of stone, but they wrote in this form of writing you can see on here that for many years, until about the 1850s, we had no way of accessing. And once these texts were deciphered, it became apparent that there was a huge amount of mathematics that the Babylonians had managed to get their heads around. So a few things we ought to know about Babylonian mathematics. Instead of using a base 10 system like we do, they used a base 60 system, which means that for the digits 1 to 60, they needed a symbol that would represent that digit rather than the digits 0 to 9 that we use. They didn't actually have a 0. It took a little while for 0 to enter mathematics. But they also wrote out huge multiplication tables, because if you have a base 60 system, that means there's a lot more that you have to remember, but your calculations can be quicker if you have that information to hand. If you knew, for example, what 59 times 43 was in a flash, you wouldn't have to do long multiplication or use a calculator as we do. And it's similar for the Babylonians. If they have a lookup table in which they can find out the different values, then that's going to be very useful to them when they're doing lots of calculations to keep their empire ticking over. Okay, so this is the situation. Babylon around 1700, real flourishing of intellectual mathematical life, and a real beginning of interest in geometry and astronomy and all of those kind of things. Okay. So I want to show you basically one trick that falls out of an identity that the Babylonians used to solve quadratic equations. So Babylonian multiplication was the name of the identity in the Dr. King book, and it gives you a really nice way to do 122 times 78 and other multiplications. I've chosen this one because it's particularly lovely. I think you'll like this trick. So it goes like this. Instead of trying to multiply these two numbers, I'm going to first add and subtract them. Now you can possibly see where I chose the numbers nicely here, but we add them to make 200 and subtract them to make 44. Step number 2 looks even more perverse, because what I'm going to ask you to do now is compute the squares of 244, subtract them and divide by 4. Now, you might think this is a very strange thing to do, but if you're writing up a long table of calculations, perhaps it's a shortcut if you only write down all the square numbers and you can work out other multiplications using the squares rather than having to write out every table of multiples. So imagine you know your squares really well, then you might be able to use a technique like this to speed up doing your multiplication. Okay, what do I do next? Well, I'm just going to simplify this, taking through a factor of 4. Now, because those terms are squared, that means I just need to divide each of the yellow and green terms by 2, in fact, to make this work. So this is going to be the same as 100 squared minus 22 squared. I work that out like this, and finally comes out as 9,516, which is the correct answer. check it on your calculator if you don't believe me. I think that's really nice that we can find this completely wacky looking process that uses information about squares and tells you how to multiply two arbitrary numbers. Hopefully, you're trying to figure out right now whether this is always true, whether this is just a fluke that I have chosen these numbers particularly nicely. But the hint is in the title of this talk. We're talking about identities, things which ought to be true for all values. And when we compare the process that I've just demonstrated with the identity called Babylonian multiplication, we can see where this comes from. So on the top of this slide, I've written an identity, which you can verify directly if you want in at least two ways. Firstly, you could try multiplying out both of these brackets and then doing the subtraction. That'll give you the right answer one way. Or you could in fact use the difference of two squares factorization on this expression, and you'll get 4ab in exactly the same way. So this identity here we know to be true for all values of a and b. And on the right hand side of that identity, we've got something that looks very much just like a normal product of two numbers, a times b. So this tells me if instead of working out the product directly using long multiplication or a calculator, I'd take the sum of the numbers and square it, and the difference of the numbers and square it, and take that difference, divide by 4. That will always give me the same answer. In some ways, this reminds me of the number tricks that you might see early on when you're first studying algebra in year 7 or year 8. Why does it always work? Well, the algebra is always the answer to that, and this is a particularly nice example. I'm going to put a problem up on the board now. You don't have to answer it immediately, but see if you can get it out at the end of the lecture. Can you use this same method to solve this problem, 253 times 53, using the Babylonian multiplication algorithm? Now, I have been a little bit glib here because while this is a nice application of the Babylonian multiplication identity, I'm not entirely convinced, having looked into the history of this, that this is really what they did. It's a nice trick, but there are more effective ways of multiplying numbers, even if you are a Babylonian working in base 60. But the reason the Babylonians cared about this kind of thing is that this was part of their approach to solving problems like this. X plus y is 8, x times y is 15, find x and y. Now, I've picked easy numbers again so that we can see that one solution of this would be 3 plus 5 is 8 and 3 times 5 is 15. But obviously the Babylonians want to solve this problem in general. They want to know if x plus y is b and x times y is c, how do I find out x and y? And if we were to spend a little bit more time talking about this, we could go into the detail of how they used that information to figure out what was going on. Okay, this is where we're going to take one of those leaps. So that's Babylonian mathematics, at least a tiny part of it. They had a whole bunch of other interesting things that we could spend more time talking about. But we're going to leap across to Egypt, first of all, and then India as well. So Diophantus and Brahmagupta, they were working completely independently, separated by many, many miles, and also several centuries. Now, Diophantus was an Alexandrian citizen. He was working in the 200 AD kind of time, maybe 200 to 300 AD. We're not entirely sure of the dates of his birth and death. And he was interested in solving equations with whole numbers. And it turns out that later down the line, mathematicians in India and China take algebra further than the Greeks ever did. So Chinese mathematicians went on to solve higher degree equations. So instead of quadratic equations, they went on to look at cubics and quartics, but trying to solve them approximately. That was an area where they had great success. Whereas Indian mathematics stayed a little bit closer to the interests of the Egyptian Greeks and Greeks, looking at solving equations where we're looking for whole number, typically positive solutions to the equation. So I've grouped these two identities together. On the top, we've got Diophantus's identity. Doesn't look particularly exciting. I mean, on its own, it doesn't reveal very much necessarily unless you've got a bit more context about what's going on here. But Diophantus was trying to solve equations somewhat like Pythagoras's formula, trying to find integer solutions to those kind of things. So if he could find relationships between squares and products and generate other squares from them, that was something that was very interesting to him. And then underneath, we've got Brahmagupta's identity. Now, Brahmagupta was working much, much later, sort of around 600 AD in India. Now, I've highlighted, or on this map, it's highlighted roughly the kind of part of the world where he was working. And the astute amongst you might have already spotted that Brahmagupta's identity really is a supercharged version of Diophantus's identity. So if we let n equal -1 in Brahmagupta's identity, then everything falls out and we just get Diophantus's identity back again. So Diophantus was doing work trying to solve particular types of equations, and in particular, he was interested in equations that look like this. X squared minus ny squared is equal to 1. And the reason he was interested in solving these kinds of equations is because if you can solve this kind of equation, then it should give you a route to being able to solve lots of other equations of this type. So the simplest quadratic, or most famous Diophantine equation with power 2 involved is going to be a squared plus b squared equals c squared, Pythagoras' theorem. But after that stage, you might start wondering what other formulae, what other equations can we solve which have answers which are whole numbers. And this is a natural place to start looking. So one example of that, for example, let's take this one here, and I'm now going to try and change the way I'm showing the screen so that I can show you a little bit more in detail how this works. And the thing is, we want to solve this with only integer solutions. So if you get stuck on a maths problem, one nice thing that you can try is to have a guess. And I'm going to have a guess that isn't very good, but which gets us closer to solving this equation. So let's try this. Let's try 10 squared minus 92 times by 1 squared. So in this equation, we're letting x equal 10 and y equal 1. And we're seeing whether we can get a solution out like this. Well, obviously it doesn't work, because when I do this, instead of getting 1, which I wanted, I'm going to get 8. That's a pity. It doesn't help. Now, the thing that Brahmagupta noticed is that you can actually use this equation, you can use this non-solution to get closer to an answer to the original question we were trying to work out. So although that doesn't work, it's not completely useless to us. So the ingenious idea, which relies on the identity I showed you just a moment ago, is that we can somehow mix this solution with itself and find another solution that might be better, might get closer to the thing that we're trying to solve. Okay, so how does this work? Well, what I'm going to do is define a new guess for x. Okay, so what I'm going to do is I'm going to take x and times it by itself. And then I'm going to take 92, lots of this, times by my original guess for what y was. So we'll take y and square it here and see what we get. So this is producing a new value for x given an old value for x. And I'm going to also try and guess a new value for y. I'm going to work that out by doing x times y and add it to itself. So do that twice and see what we get from that. Now, when I do that with these particular numbers, I get a new set of values for x. So x prime work out as 10 squared plus 92, which is 192. And y prime will work out as 2 lots of 10, which is 20. Okay, so the clever thing about Diophantus's idea is that if we know all of this information, we can write down for these new values that we've got 192 squared minus 92 times 20 squared is equal to 8 squared. And that, it turns out, comes directly from Diophantus's identity. And then finally, almost finally, we can divide through by 8 squared, and we end up with this. Okay, now this doesn't look much better, but remember what we were trying to do in the first place. So in the first instance, what we're trying to do is solve this equation up here. We're trying to solve x squared plus minus 92y squared is equal to 1, where the answers have to be whole numbers. And we've got really very close already, just with this one idea of creating a new solution from the other using an identity that Brahmagupta found out. So have a look at this final answer down here. What we've got is now 24 squared minus 92 times 5 over 2 squared is equal to 1. And you might object that you haven't really solved the problem yet, but I've got a lot closer, because now I've got an almost integer solution to this equation. Here, 24 for x and 5 over 2 for y are almost solving this equation correctly. And if I do the same process one more time, then hopefully this will give me an integer solution to the equation I was looking to solve. Right, let's go back to sharing the presentation. So that is Diophantus and Brahmagupta. They made very significant contributions to other areas of mathematics, but there's just one problem that we can approach thanks to their ingenious identities. Okay, I've only got a couple more mathematicians that I would like to talk about today and finish up with. We're going to talk about Cardano, and then we'll talk very briefly about Sophie Germain, and then I'll open it up for any questions that you might have. So Cardano, who had a fairly tragic life, it must be said. He was very desperate to be a trained doctor, and indeed he went on to become a very respected physician, but initially prejudice about having unmarried parents meant he wasn't admitted to the Milan Medical School. He also had other tragedy in his life in that his own son was executed for committing crime, and Cardano himself was tried by the Inquisition for heresy, getting off with a light sentence, but nonetheless a pretty difficult personal life. Despite all of that, despite working really hard to become a respected doctor, despite all of the personal tragedies involved, he also managed to make a significant contribution to our understanding of algebra, at least in the Western Hemisphere. So his identity is the one that I've put up at this point, and on the face of it, it doesn't look like it's telling us anything. You could prove this very easily just by expanding both sides of this equation. If you've done the binomial expansion, you'll know how to do the left-hand side very easily, but even just multiplying the brackets together doesn't take very long. And then regrouping some of the terms, it looks like this. So you might wonder why Cardano would have his name attached to something that looks so trivial. And the reason is that this approach cracked open, or rather this identity cracked open an approach to solving certain cubic equations. Now, at school, you've probably solved equations that have x squareds in, or maybe you've solved some cubic equations with x cubed in, maybe which don't have a constant term on the end. But this equation that I've put up now, we're going to try and solve for x, so we're trying to find what value of x makes this true. We don't care about whether the answers are whole numbers or not this time. We want to know, are there solutions and how do we find them? How can we find the x? If I give you L and M, can you tell me what x would be to make the expression on the left-hand side equal to 0? Okay, so people struggled away at this for ages. I told you already, the Babylonians solved quadratic equations. They could solve those. And now in Western Europe, we don't really have much of an idea how to solve these until the 1500s. We're going to try and find out what x is worth, and the ingenious idea that Cardano had, and I really think this is sort of next level moment of ingenuity, is just to say, well, let's set x equal to a plus b. And the reason this is ingenious is because he has no idea what a or b might actually turn out to be, but let's set x equal to a plus b. And it turns out he also is going to incorporate another condition, which we'll talk about more in a moment. But because he has introduced a new variable, Cardano is at liberty to choose the relationship between a and b so long as he can create any possible value of x. So this condition in yellow satisfies that requirement because he can solve, he can find a value of b and a that will work in this case. So once we do this, the equation that we're trying to solve looks slightly different. Every time I see an x, I replace it by an a plus b, and I've got some work to do to expand this. So once I expand this a bit further, we get a cubed plus b cubed plus 3ab a plus b using the identity. So the part in green has come directly from the identity that Cardano is using, plus L lots of a plus b plus m. Now this is where Cardano's condition is so clever, because what he's doing is he's saying, because I chose x to be equal to a plus b, I also can tell you a relationship between a and b for free, and I can choose that relationship to be to my advantage. So if I set my equations up in such a way that 3 times a times b has got to be equal to minus L, then the middle two terms in here, this one here and this one here, are going to cancel out. So the idea is that if we also have this additional condition that 3ab is equal to minus L, then this term and this term will be the same size but of opposite signs, cancelling out, leaving an equation that looks like this. Now, for the sake of time, I'll leave out the detail here, but this equation can then be transformed into effectively a hidden quadratic, which you can solve. So Cardano's method gives you a way of solving all cubics that look like this in the first place. So that's why he gets his name attached to this particular identity. Okay. Having lost a little bit of time there with the tech issues, I will very briefly talk about a final character, which is Sophie Germain. So this is one of the final identities in the list. And on the face of it, it looks like one of those sum of squares identities. So a to the 4 and b to the 4 are clearly squares, and so is 4a to the 4. So if we've got some additional structure, we can factorize that sum of squares, in this case sum of fourth powers as well, in this nice way. And it turns out that this identity is the weird counterexample to the question of when is an expression like this irreducible. So what do I mean by this? Well, if we've got an expression like x squared minus 9, then I can reduce it by factorizing it out. I'm not trusting the switch to the other device, hence the very dodgy writing on here. So in this case, when n is 2 here, we can reduce this in this way. We can also do things like x to the 6 minus 4. That can be reduced as well. We can write that as x to the 3 minus 2, x to the 3 plus 2. So we've got another way of writing the same expression where we've managed to write this in lower terms as we go along here. And so the question is then, well, how do we know whether we've found all of the possible ways of reducing things? Well, if we've got a is some kind of nth power, as we've got here, so if this is a square in the case of x squared minus 9, well, that's x squared minus 3 squared, then it's going to be reducible. And we also saw that that isn't quite good enough, because we could have, in this case, this written as a square, and this is a square. We could also factorize this as sum of square, as difference of two squares. But it turns out that amongst all of the different ways that you can write x to the n minus a, they're all sort of this type, where we're factorizing some power of a in here. So it's either of this type, where the number on the end is some nice power, or we're actually doing some kind of expression which is secretly of this form. So Sophie Germain did a whole lot of work in number theory. She actually had a decent crack at proving Fermat's last theorem as well. But one of the things that she's got her name attached to now is this identity, because it tells us something about when these kind of expressions are irreducible and when they're not. Right, well, I'm going to stop there. I should probably, at some point before the end of this recording, show the bibliography and the sources, but I'm going to break off at that point just with some final concluding thoughts, which is to say that the journey through the mathematical world, which has been a journey across many different countries and through lots of time periods, hasn't come to a stop now, although the material I've drawn on for this lecture comes from 3,000 years ago up to about 200 years ago. Never more than in the present day has mathematics been a global endeavour. People are working together across the world to try and push the boundaries of mathematical knowledge. They're trying to prove statements that are true for all possible values of the variables day in, day out. That is the bread and butter of proving theorems in mathematics. And it really is an endeavour that is very human, and one which I hope some of you will go on to be part of. So I hope you enjoyed the thoughts I have gathered together today. Apologies for the technical issues I had partway through, and I'd now like to open this up for any questions that we have.
I'd like to thank you so much for an absolutely fascinating hour, and hopefully you'll come again to do some lectures for us at the Oxbridge Network. There is one question from Talal. Is mathematics a discovery or an invention? What an interesting question.
This is a very classic question, and one which I actually noticed as I was talking, the point at which someone would wonder that. I think that we set out systems which we investigate, and we create those systems and we investigate the consequences of them. So because we are not necessarily granted infinite foresight, we cannot predict all of the outcomes of the decisions we make in creating mathematical systems. I think it feels a lot like discovery when you go down the track of proving something, when you go down the track of investigating patterns. I think there is something out there that it feels like you're discovering. And I think also the more that the mathematics you're studying seems to tie in with our experience of the real world, whether that's through number or whether that's through physics, the more it feels like a discovery, because the more it feels like it maps onto something that exists already. I think it is possible to think of mathematics as invented. If you invent a game, for example, and you discover the rules, discover the consequences of the rules of that game in terms of winning strategies, that feels like you're inventing something in order to discover something about it. But I would say the main aim of mathematics is to discover interesting truths about mathematical systems and potentially see how they map into the real world.
Okay, hopefully that answers Talal's questions.
I realise it's a bit of a hedge, saying a bit of both, but mostly discovery is where I probably fall on that question.
It's quite a philosophical question, isn't it, Mr. MacArthur? I think we'll wind up now. It's 17:59 and we've made full use of the hour that we've had. So once again, Mr. MacArthur, did you want to put any sources up? Did you want to put any...
Oh yes, just for the benefit of the recording. That's a good point.
Yeah, just in case anybody wants to explore further, that would be useful.
So there's a bibliography. I didn't actually end up talking about the Babylonian calendar, but if I had, then there was some information in that book. All of these are very good books, and at least one of them is available in the school library. Hopefully all of them I haven't checked though. And then for the benefit of the recording, there are the image sources, but that's not very exciting to read. So I will
Okay.
finish it there.
Thank you very much for that. And obviously, food for thought for anybody that's actually thinking about personal statements and that's also thinking about exploring mathematics in a bit more detail. And we will be inviting you again, Mr. MacArthur, to join us for the Oxbridge Network. So thanks very much for that, and hope everybody has a good evening, including you.
Thank you. Goodbye.
Thank you. Bye-bye.